So the talk is about hyperbolic groups of Fibonacci type. This is a particular subfamily of cyclically presented groups. And recent work of ours extended the classification result on which of them are hyperbolic. Well, except for these two groups here, H94 and H97. So I'm going to tell you, some of the ideas that is involved in this classification. I haven't assumed any knowledge at all because I didn't know who was going to show up. So I prepared really basic material, which somehow made my talk, it's going to make my talk very long. But anyway, let's get on with it. So the outline is to tell you what the group presentation is, and the main combinatorial object that I use in this class, in this work is Van Kampen diagrams. So I'm going to tell you what that is, and then tell you about cyclically presented groups, and then the main result in this work. Okay, so let's begin. So really from the basic, what is a group? For those who are new to group theory, it's just a set together with an associative binary operation, and the property is that we want an identity element to exist in the group. So there is a unique element in the group, so that when you multiply it with any other element in the group, you get the same element. So it doesn't it doesn't change the element when you operate it. And there's a unique inverse also for every element in your group. So I have two examples: the integers and the cyclic group of other 5. If you have a set X, you can form the set X plus or minus 1, which in this talk you can think of as an alphabet. So a word in this alphabet is just a finite expression of this form. That's what a word is. So you have a set S, and you throw in the inverses of that set S, and then you call this an alphabet. And a word in your alphabet is just a finite expression of this form where the AIs are from your alphabet. So you think of this AI as letters in your alphabet, just like you have the ABC. And then we say that this word is reduced if there is no occurrence of something like that. So there is no consecutive terms where one is the inverse, the formal inverse of the other. We say it is cyclically reduced if it's reduced mod K. You can do it if you do this mod K and it's still reduced. So every cyclic permutation of your word is reduced. I have some examples here. So here you have a word which is not a word in this alphabet because it's got a Z here, and I haven't got Z in my X. So it's a word, but not a word in this alphabet. So if you go to the dictionary of words in this, in this alphabet, you wouldn't find this because Z is not in this alphabet. Here is a word which is not reduced because it's got this X and S inverse. Here is a word which is reduced, but it's not cyclically reduced because it's got X inverse here and X here. So if you cyclically permute, these are going to cancel. And this is an example of a cyclically reduced word. So, and there is a notion of length. The length of a word is, the first thing you do is to, reduce the word. So cancel everything that's, that cancels out. And then you take the count how many letters you have in your word. So in this case, these two cancel, and then you have 6 letters left, 2X and 2Y. Okay, so now let's define what a free group is. A free group is just a set again. So a set of reduced words this time. So you have your alphabet here. And the free group on X is a set of reduced words in this alphabet together with an operation. So the operation is concatenation plus reduction. So you first so how do you multiply 2 elements in your group? You just concatenate them, you just join them, And if there is any cancellation, you cancel that, you reduce the word. The identity element is the empty string, and the inverse of a word is of this form. So here's an example here. Here you have a U and a V. When you combine them, you have Y inverse cancels with Y, and then, so this is what is left. So this is what you get when you concatenate this and reduce. And it's a theorem that every group is a quotient of a free group, of some free group. Okay, so if you have a group G, which is a quotient of a free group on X, then this means that there is a normal subgroup of your free group, such that when you quotient the free group by n, you have your group G. So it turns out that, so what this means is that in your free group, you are killing every element in n to get G. So when you kill every element in n, you get your group G. It turns out that you don't actually have to kill every element in n to kill n. There is some subset of n, we'll call it R in this case, such that when you kill R, you have actually killed the whole of n. This happens when n is something called a normal closure of R. That is, this is the smallest normal subgroup of your group containing R. In that case, we say that this is a presentation for your group G. So you put in the generators of your free group X, and then you put in that subset of n, such that when you kill it, you kill the whole of n. This is what we call a group presentation. And we say that P is finite if these two sets are finite. For my talk today, I'm only going to talk about finite presentations. Okay, so here are some examples. So this is a presentation of a free group of rank 1, or the integers. So every element in this group is just R of X, positive or negative. And you can see a clear isomorphism from this group to Z. When you think of Z as integers under addition, there is a clear isomorphism. Just takes S to its power. Here is a presentation for free abelian group of rank 2, Z cross Z. And here is a presentation for Z2 cross Z2. I should say, if you have any question at some point, just let me know, or you can write things down and let me know at some point. Right. So if you have a set R, you can form something called a symmetrized closure of R. This is just the set R together with all the cyclic permutations of the elements of R and their inverses. So you have your R, for example, XY, you throw in all the cyclic permutations of this set, and then the inverses. This is called the symmetrized closure of R. So I would like everyone to try and write down what this is. As a hint, unless you already know what it is, but as a hint, it's going to contain 8 elements. So there are 4 cyclic permutations of this guy, and then you throw in the inverses of the 4 of them. So you're going to have 8 things. So it's if you didn't get the definition, it's worth trying to write this down. I'm going to use it later. So okay. So now suppose we have a group which is defined by a presentation. What this means is that your G is a quotient of the free group by the normal closure of R. And what this means is that if the W is a word in your free group which is trivial in G, then W has to belong here, because this is the set of things that are trivial in your group. It turns out that the following is true. So here's a lemma. It's called the Van Kampen lemma. If you have a word in your free group which has length greater than 0, then W is trivial in your group if and only if W belongs to this normal subgroup. We've seen that. But then if and only if W can be written in this form. This is the key thing that I want to, that leads to a Van Kampen diagram. So if and only if W admits a Van Kampen diagram. So the point is that if you can write your W in this form, then it does admit a Van Kampen diagram. I'm going to tell you what this is in the next slide. So what it's saying is that your W can be written as this product where the Ri's belong to the symmetrized closure of R. And we call the minimal alpha for which you can express W in this form as the area of W. It's called area because it does correspond with something that looks like area in your Van Kampen diagram. So this equality here is equality in the free group. It's just writing W as a word in the free group. This is not equality in the group. It's in the free group. So here is what happens. So suppose your W has this form, then you can, for each Ri, you have a face. So a Van Kampen diagram is a two-dimensional complex. It's just a piece of the plane. It's a disk, a topological disk, where each face, which is somehow triangulated, where each face is each face of your two-dimensional thing corresponds to each R here. So for each R, I have a face, and for each UI, I have an edge going to that face. So this word here, so U1, R1, U1 inverse will read U1, R1, U1 inverse. And you do the same for the next one up to alpha. And then you can see that your W can be read from this figure by just going around everything and coming back to it. So this is what we call a Van Kampen diagram. You can see that it's a topological disk. So this is a disk, this is a disk, and that's a disk. So I'll give you an example. Here's an example. So you have a presentation for the free abelian group, and I want to show that I want to draw a Van Kampen diagram for this word. We already know this word is trivial because it's a commutator, and everything commutes in this group. So it's definitely trivial in the group. And the Van Kampen lemma says that it can be expressed in this form. And this is what we do here. So I've expressed it in this form. And if you did the exercise in the previous slides, you will see that these words belong to the symmetrized closure of this. And then you can then draw the Van Kampen diagram. If you draw the Van Kampen diagram, you get something like this. So initially, the first step of this Van Kampen diagram is to get something like this. And then you identify things that can be identified in your diagram. So for this one here, you have y, x, y inverse, x inverse, y inverse. So that's y, x, y inverse, x inverse, y inverse. This one is the same. So you do y, x, y inverse, x inverse, x inverse, y inverse. That was going to give you this. And you continue with this will be that, and this will be that. So that's what you have. And then you identify things. I've already identified everything to get this shape. And then you can see that this has got 4 faces. It does correspond to the number of elements in the symmetrized closure that you used. So remember, I said the area is the minimum alpha. So it could be that the area is actually less than 4, but it's at most 4. Okay, so the then function, therefore, is a map from the natural numbers to the natural numbers. What does it do? It looks at your free group on X and takes all the words of length M in the free group that are equal to the identity in your group. So it goes to the free group, takes all the words of length M that are trivial in the group, and then computes the area. The minimum such area, the maximum of such area is the image of Fm. This function is called a then function. A finitely presented group is then said to be hyperbolic if it has a linear then function. So it means that this function is linear on, on the length of the word that you start with. It's a linear function. So to show that a group is hyperbolic, one way to do that is to show that the presentation has got a linear then function. So I'll give you some examples of hyperbolic group. Every finite group is hyperbolic. Okay, so in terms of this, they are not very interested because they are all hyperbolic. The free group of rank 1, in fact, all free groups are hyperbolic. For example, the integers. But the free abelian group of rank 2 is not hyperbolic. And in fact, any group containing it is not hyperbolic. So this is some infinite family, and this is another infinite family of non-hyperbolic groups. Okay, so the key point so far is that you have a finite presentation, and it is hyperbolic if the then function is linear. This is equivalent to saying that the number of faces in your Van Kampen, so if you have a reduced Van Kampen diagram over that presentation, the number of faces is a linear function of W. So if you have so let me say it again, if you have a Van Kampen diagram whose boundary is W, then the number of faces in that Van Kampen diagram has to be a linear function on the length of W. That's the same thing. I'm saying the same thing. As a then function which is linear is the same as this what I just described. So what I haven't told you is what a reduced Van Kampen diagram is. So here's an example of something that is not reduced. So it is not reduced if it's got something that looks like. So you have two faces which has some edge in common, and that edge acts like a mirror. So if you stand here and you look this way, it's the same thing you see when you look that way. Another way to say is that if you read the label on this face, and read the same label on this face, you get the same thing. So this is acting like a mirror. What this allows us to do is to collapse the two faces, which is what I've done here. So if it's possible to collapse some faces to reduce the kind of area, we say that the diagram is not reduced. Okay. Right. Now I'm going to tell you about cyclically presented groups, which is the main object of my talk. So you have a set X here, which is X0 to Xn-1. This is the set I'm using. And you have so this is the generators of your free group. And there is some automorphism, theta, and this is called the shift automorphism. It just takes this X0 to X1, modulo n. So a cyclic presentation is a presentation of this form. So you have your generators, and then you have a word W, and they are all, so this is an example of what is called a balanced presentation. It's got the same number of generators as relations. But this is described by just picking the word W and then applying this automorphism to the W. Everything here is, the subscript here is all modulo n. So you take your W and you apply this automorphism. We usually take W to be cyclically reduced, but it can be any word, it doesn't matter. And we say a group is a group with a presentation of this form is called a cyclically presented group. That's it. And here is this is the kind of presentation that I'm interested in, the kind of cyclically presented groups I'm interested in. It's this family called the groups of Fibonacci type. So for M and K are integers, you have this family of cyclically presented groups on W here is just this word here. I'll give you some specific examples. There is a Conway's Fibonacci group at F2N. This is where you take M to be 1 and K to be 2, and you have this presentation here. It's called Fibonacci because you look here on the subscripts, you have 0, 1, 2. So you add the first two subscripts, you get the next one. And then there is this Radsky groups, S2N. It's almost like this, but then the M is 2 and the K is 1. And then the Gilbert-Howe groups, I mentioned two groups in my abstract, which we couldn't classify whether they are hyperbolic or not. they belong to this family. And then this is just some, M is the parameter here and everything. So this is the presentation for the Gilbert-Howe groups. And so the big question that I'm asking in my talk is, when are these groups hyperbolic? So it's a question that people have been interested in over the years, and there are some classification results already known. And here is what is known. So I want these parameters K and B. I'm setting K to be, so I'm setting A to be K and B to be K minus M. And I'm describing the results based on these two things. So if A is congruent to n over 2 mod n, and or B is the same, with the group is hyperbolic. Sorry, the group you get is a cyclic group. And I told you before that all finite groups are hyperbolic. So this is hyperbolic. The same happens in this case when A minus B is 0 mod n. The group you get is cyclic. So again, it's hyperbolic. It turns out that when A plus B is 0 mod n, you get this group, and it has been shown to be not hyperbolic. This was done in 98 and 86. The Fibonacci groups as well are hyperbolic. This was again 98, similar result, topological result that was used to show. It was shown that these groups are fundamental group of hyperbolic manifolds. So they are hyperbolic. But recently, chalk shows also that for the odd cases, so this is for the even n cases, and this was for the odd n cases. And the Gilbert-Howe groups of this form, the answer is yes. And here, this was a recent result by myself and Williams, and we showed that these groups are not hyperbolic. And again, there is some characterization of groups called thesis. This is again something that has to do with Van Kampen diagrams of these groups. We showed that if none of these conditions hold, then the group satisfies the thesis, and so it's hyperbolic. So the only case that is really left open is this case here, and this is what I want to talk about. So the rest of my talk is really to describe our result, which determines when these groups are hyperbolic, thereby completing this classification, except for the two groups that I mentioned earlier. And in fact, the theorem that we have is the following. So suppose those conditions hold. I've told you what these conditions are. These are exactly the conditions that are in here. Suppose these conditions hold, then the group is hyperbolic. So there are three cases to this. There are three cases to be considered. This is when n is between 2 and 12. And the proof of this for this case. Sorry. There's something here. I'm only considering when n is greater than 12. Just for this talk, but the classification is known for all cases. But for this talk, I want to concentrate on when n is 12, and this is when all these groups here are hyperbolic. If you go below 12, there are some that are hyperbolic and some that are not. So I don't want to talk about that today. So there are some hyperbolic ones and some non-hyperbolic ones. Between 12 and 7p, these are all hyperbolic. I should have said this in the slide. These are hyperbolic, but it was proved computationally using computational software ABMag. And the case that I'm really interested in is the case where n is greater than 7p. So 7p will be 21 when p is 3 and 28, 35. And this is theoretical proof using Van Kampen diagrams. And in fact, something that I call the ant-lane arguments. And I'm trying to get my camera to leave this the way. Okay, that's good now. So I'm gonna describe the proof of this case using Van Kampen diagrams. So remember that the presentation of these groups, they have all the relators have length 3. So if you go to the Van Kampen diagram that I described earlier, this is all going to be a face with 3 vertices. So I'm going to have 1 vertex here, 1 vertex, and then these are letters, 3 letters, because all the relations here have, in my case, is going to have length 3. So every face of your Van Kampen diagram looks like that. It's a triangle where you have some xi going to xi. So you have, every face looks like this for some I. And if you look at this face, you will see that there is a source here, and there is a sink here, and this is neither a source or a sink. So I'm labeling these corners by x. It's not the same x I had in my previous slide. This is just a notation now for this corner, x. I'm labeling the sinks by y. I'm labeling the sources by z. This is what this is about. So what it means is that if you go to your Van Kampen diagram and look at the length of a vertex, so if you look at an interior vertex of Van Kampen diagram and look around it, you're going to see something like a word. You're going to see a word, which is a word in x, but you're going to see z and maybe z or x and so on. You know, it's going to describe a word in x, y, and z. So it's going to be a z here if it's a sink, if it's a source again, but if it's you can't have a sink because you've already have h going out to the vertex. So it cannot be a sink here. It cannot be y here. It can be x or z. Okay, so but it turns out here that you cannot have an x. So you cannot have an x and then the next one is s. You cannot have a subword of that label, which is xx. The same, you cannot have yxy because y is a sink. You can have an x, which is neither a sink nor a source, in between 2 sinks and in between 2 sources. So these things, you can't see such a thing. This one here is really because I'm assuming that the Van Kampen diagram is reduced. But this one is kind of clear. It's just what I've explained. So again, we want to describe when these groups are hyperbolic. Then you have your Van Kampen diagram, which is reduced, and you try to use it to find out about this. Okay, so I'm going to describe a curvature in my Van Kampen diagram. So it's a planar, it's a topological disk, and I can use curvature arguments. The Gauss-Bonnet theorem tells us that, tells us what the sum of the curvature of such a figure is. It's the Euler characteristics times, well, 2 pi. I'm describing the curvature to be, this is how I describe the curvature of a face. If I have a face, the curvature of that face is minus 180 plus the sum of angles in that face. So I have my face, which is the face of a Van Kampen diagram, which is a triangle, and I assign some angles at the corners. And then I describe the curvatures to be minus 180 plus some of these angles. It's a consequence of the Gauss-Bonnet theorem, like I just mentioned, that if we can show that the sum of the curvature in the interior vertices is less than or equal to 0, and the sum of the curvature, I missed out curvature here, there should be a k here, on the faces is less than or equal to minus number of faces, then G has a linear density function. So if we can achieve this, then we know that our group is hyperbolic because it's got a linear density function. So again, you have this is for any Van Kampen diagram over your presentation, any reduced Van Kampen diagram. You can assign the angles anyhow you want, but it needs to work. This density function has to be linear for any Van Kampen any reduced Van Kampen diagram. Yeah. So the choice of angle assignment is up to you, but this better works for any reduced Van Kampen diagram. Okay, so this is the assignment that I use. So I look at the vertex of degree Q in my Van Kampen diagram, and I assign angle 360 over Q to all the corners at that vertex. And then I look at the vertices that are boundary vertices, I assign angle 29 to them. So this is the assignment I want. By this assignment, you see that every interior vertex has to have curvature 0 because of the way it's described here. The sum is going to be 360, and when I subtract 360 from 360, I get 0. It's going to be 360. So we have that this condition here is satisfied for my interior vertices. The problem is here, is the faces. And if you look at a face, so I differentiate two faces. There are the faces I call the black faces and the one I call white faces. I'm not being racist on the faces, but it's just for me to be able to calculate this, this curvature. So these black faces are going to have positive curvature. They are going to have positive curvature, while the white faces are going to have negative curvature. So this is an example of what happens. And the thing I'm going to do later on is to try to sum over, try to redistribute the curvature from the white faces to the black faces. The negative curvatures, I'm going to move them because all I need here is really -1. So I don't need up to -24. So I'm going to move some of this negative curvature to the black faces so I can have my result in the end. Okay, so a face is called a black face if it is incident to an interior vertex of degree less than or equal to 6. Otherwise, it's called a white face. So if it's got a vertex of degree less than or equal to 6, we call it a black face. So the curvature of a face, so if you have a white face, so it's got no vertex of degree less than or equal to 6. So the smallest degree of a vertex incident on that face is 7. And from the way I assign my curvature here, the corners are going to have angle at most, at least 72. Sorry, at least 52, because I'm going to divide 360 by 7. And then I have, so you want to choose this angle to be as big as possible because you're trying to get this curvature to be very small. So you better choose the biggest angle which you can get. And in this case, I get 52 because the smallest vertex has degrees 7. The smallest degree of a vertex is 7. So I have 52, and the curvature is -24. So we are fine with white faces, but the black faces, we don't know. So there is an isomorphism between this and this. I can exchange B with A. That's the point of this isomorphism. So instead of saying that either A or B holds in my theorem, I can just assume that A holds. This is the point about this isomorphism. I can assume that A is equal to that. And then there is a lemma here. This lemma says that if I have a vertex of degree less than 7, so if I assume that this condition holds that n is greater than 7p, if I have a vertex of degree less than 8, then it has to have a label of this form. So it's the label, if you read around the vertex, you're gonna see is Z3. So it's gonna be all sinks, all sources, Z3, Z6, Z4, or Z4. This is all you can have. This is saying that the vertex has to have degree 3 or 6 or 4 or 5, but the label around it has to be all Z. You can't have anything else. So this condition tells us, enforces that. So here's an example. Here's an example where the interior vertex has got degree 3, and that lemma is telling us that it has to have Z here, Z here, Z here. So these are all going to be sinks. That's from that lemma. And this is another crucial lemma which we use. This lemma is telling us that if I have a Z here, then clearly this cannot be Z and this cannot be Z because every face has got that corner, one corner with Z, one with X, and the other with Y. So I've got Z here already. This cannot be Z, this cannot be Z. But the most important thing here is that it's telling us that even this one cannot be Z. I wish I could draw now, but maybe it's going to take more time. So if this is a Z, assume that this is a Z, this is going to be a source here. Because this is a source, I have an edge. Of course, I have an edge going this way and edge going that way. Now, this is also a source. I have an edge going that way. This is going way. Now, this edge here, an arrow can go either direction. So without loss of generality, we can assume that it's going this way. What it means is now that this is a sink, and this is also a sink. Therefore, and this one here, this is the important one, this is neither a sink nor a source. The same thing with this one, because I have an arrow going this way and going that way. So this is neither a sink or so this will be labeled by X, and this will be labeled by X as well. And we say that this cannot happen. If the Van Kampen diagram is reduced, then you can have XX. So this is the proof of this lemma. So whenever we have a black face, so this will cut, right? So I told you that black faces are faces where there is a vertex of degree less than or equal to 6. So this is why I've colored this one black. Right. So this lemma tells us that this cannot be Z, and we know that this place is not Z, this place is not Z. So this face here cannot be a black face. It's got a vertex which has no Z here, so it cannot be degree less than or equal to 6. It has no Z here, so it cannot be degree less than or equal to 6, and so on. So it's got a white face adjacent to it. So by that lemma here are some configurations of white and black faces that are impossible. And look at this, for example. Let's explain this. So this is a white face bounded by these 3 black faces. This cannot be a vertex of degree less than or equal to 6 because it's incident to a white face. And the same thing with this and that. So because this is a black face, it means that this has to be a vertex of degree less than or equal to 6. The same thing that happens here. You conclude that this has to be a vertex of degree less than or equal to 6. Same thing here. Now, by that lemma, which we just saw, this is a Z here, so this cannot be Z. This is Z here, this cannot be Z. This is Z here, this cannot be Z. So you have a face where none of the corners can be labeled by Z, which is impossible. And if you use the same argument, you conclude that none of this can be possible. Okay, we use this later, but we'll see. Okay, I think I need to be faster. So like I said, the point here is to kind of redistribute these curvatures on the white faces to the black faces. So in the end, I want the sum of the curvatures to be at most minus the number of faces, for us to use that lemma to show that the group is hyperbolic. So I'm going to use something called ant-lane argument. The point is that I have this following traffic rules for ants. So I place ants on the Van Kampen diagram. So this is really, okay. So let's go through this. So I have consider an ant taking a walk on D and obeying the following traffic rules. So an ant begins its journey at the interior of a black face called home. So I put an ant in each of the black faces in the Van Kampen diagram. And the ant is never supposed to walk across a boundary. So your Van Kampen diagram has got a boundary. The ant cannot cross a boundary. But the thing is that if this home is adjacent to a white face, then the ant must walk into that white face. So an ant must move out of a white face into an adjacent white face if F is adjacent to a black face different from home. So it comes out of home and enters a white face, and then it looks, is there another black face which is adjacent to this white face? If yes, it goes into the next white face. If there is no black face, then it doesn't move, it just stops there. So it has to move into an adjacent white face only when there's an adjacent black face different from home, okay? And an ant is not allowed to backtrack. So these are the rules. One thing to remark here is that an ant following these rules does not visit a face twice. It's very important. I'm not going to explain why, but that's true. So you can kind of picture this in your mind. So think of these places as the black faces, and the ant is actually just walking on the white faces. So think of this brighter places as the white faces and the darker regions as the black faces. Actually, if you look here, you can see that this ant here looks like it's sleeping. But it's okay, it's not disobeying the rules. The rules didn't say you cannot lay on your back. It just says don't backtrack. So yeah. So think of this as your black faces, and the ant just walks on the white faces. And this is a definition. Let's do a formal definition. So an ant walk is a set of white faces in the path of an ant following the rules that I just described. So an ant lane, on the other hand, is a set consisting of home and all these white faces in the ant walk, and together with all the black faces adjacent to these white faces. So you have your white faces and all the black faces adjacent to them. That's the point. This is what we call an ant lane. Okay, a white face is called a junction if it is not adjacent to a black face. So you look at a white face which has no black face adjacent to it, we call it a junction. And an ant lane is maximal if it's not properly contained in another ant lane. It's kind of basic definition. Okay, so I'm going to try to write this in word, kind of describe what I just said. So there are many possibilities. In fact, 4 of them. This is when I have only one black face. This happens when the ant is, the home of the ant is where it cannot leave the home. The only reason why an ant cannot leave a home is if there is no white face adjacent to it. And this will mean, this will mean that maybe there is a boundary where it cannot cross, or, there are black faces everywhere. So there is no white face to move into. That's the point. So you can have this possibility, but you can also have a possibility where the ant actually walks into a junction. This is where there is only white faces adjacent to it and it cannot move. So this is like BO is the home of the ant. Ant starts from the home and walks into the white face, and then it looks, there is a black face adjacent to this white face, different from home, and then it moves into the next white face. And it looks, there is a black face adjacent to this white face. It continues to move until at this point when it now moves into the white face and there is no black face adjacent, so it stops. Here, it is the case where it has the same thing up to this point where there is nowhere to move. So it's at this white face here, and it doesn't see any other white face to move into. So it's stopped there. This usually happens when there is a boundary edge. This happens when there's this WB is a junction. And there's a third possibility, which is when it gets to this point, when it moves into the next white face, it sees 2 black faces, so it can no longer move. So there is no boundary, there is no white face. What it sees is the 2 black faces, and then it's stopped. Okay, but so if you count the number of white faces and black faces, you see that the black faces have to be equal to the white faces when there is a junction. And when there is a boundary, the white faces has to be 1 less than the black faces. And when there is 2 black faces at the end, then you have to have that the white faces are just B minus 2. If you just count what number of black faces and white faces here, you see that I have 1 more black face here and 1 more black face here. So you have 2 more black faces than white faces. And there is a lemma that an ant lane contains at most 1 junction. We've just seen what, it's only in this case when you have 1 junction, and all these ones don't have junctions. And if you have a face which is in the intersection of 2 distinct maximal ant lanes, then that face has to be a junction. So the only places where ant lanes meet and maximal ant lanes meet is in a junction. A junction is contained in at most 3 maximal ant lengths. So what we're going to do is that we're going to look at these maximal ant lengths and we glue them together along their junction. We don't want any intersections at all. We don't want any face common to any, two maximal ant lengths. So we glue them together if they have a common junction to form this set. So this set is just a set of maximal ant lengths where any two which have a common junction have been glued together. This is exactly what this is saying. So if L and L prime are in L, and L is contained in L prime, okay, I didn't write this properly. This is not properly stated, but it's just saying that there is nothing contained in the other, there is no intersection. That's the point. So this is the maximal ant lengths and joint ant lengths where there are no intersection. Okay. The point is that I want to calculate the curvature of this set, and I want to sum them. If I have intersections, I cannot sum them. That's the point of L. Okay, so we have from what I described earlier, we have different types. We have type BB, where the black face and the white face have the same number, or B minus 1 or BB minus 2. This is where we have maximal ant lengths. This is where nothing is glued together. So this is exactly the maximal ant length. But this is where I've glued two things together. Remember, you can only glue things when they have got a junction. And so when there's a junction, the number of black faces and the number of white faces are the same. So when I glue them together along the junction, I lose one white face. This is why this is now B minus 1. This is minus 1. And when I glue three things together, I'm losing two white faces. This is why I have minus 2. And then if L is of type BW, from what is written here, you can see that B is, you can see that B has to be between W and W plus 2. The black faces is just at most two more than the white faces. This is crucial. Now, if you define the curvature of L, so L is in here, the curvature of L to be the sum of curvatures and of faces in L, and then you can do this calculation. So if F is if it's a face in your Van Kampen diagram, then it's either F is it's a face in one of the elements in your L or not, or it's not or is. If it's not, then it has to be a white face because all the black faces are contained in some element of curly L. And we have calculated the curvature here that is minus 24 at most. So the problem is now here. And because the elements here are all distinct, I can sum over the curvatures. And defining KL to be the maximum. So remember, we want to bound this thing by minus F in the end. So I'm taking the maximum curvature of all so this is the maximum average curvature of an element. So I pick an L, which is in my curly L, and I take the average curvature of that. The maximum is this figure. It's this KL here. Therefore, if we can show that KL is less than or equal to minus 1, then we are done. This is what I want to show. Okay, so I think this is my last slide. So here is a lemma. Suppose each interior vertex of D has degree at least 8, or label ZD. We have already shown this. This is one of our lemmas. We show that if it has degree, if n is greater than 7p, then any vertex of degree less than 8 has to be of this form. That's what we've shown before. So this condition is actually true in our case. Then this holds, which is all we want. And the idea to prove this is that you take an L, which is of type BW, and you recall that if F is a white face, then it has no vertex of degree less than or equal to 7. So the smallest degree of a vertex is 8. And when you put 8 over 360 over 8 is 45. And when you do this curvature, you have minus 45. For a black face, we take the maximum value. So it has to have one vertex of degree less than or equal to 6. So we take the smallest degree, which would be 3 in that case, and the angle there will be 120. But the rest cannot have any black corners. Sorry, cannot have, it has a corner which is not black. Therefore, it has to be at least 8. That's why I have 45 here, and you get 30 here. So the curvature of this thing is going to be 30 black faces minus 45 white faces. And then by this condition, so there is a condition that, sorry, there's a condition that the number of black faces is at most. So the number of black faces at most 2, more than the number of white faces. If you use that condition, you have that B has to be, sorry, I don't know why this is blocking my view. So the number of black faces will be at least 6. So it's just a matter of just putting, testing when B is 1, 2, 3, or 4, or 5, or 6. And when you test them, or you see that the curvature, this is satisfied, except in the cases that I described before, except in the cases where you have this sort of things happening, which doesn't happen. This thing cannot happen. For example, this is where you have glued 2 maximal antlanes. Sorry, 3 maximal antlanes. So this is a maximal antline here. So you have a black face. So call this your home, ant home, for example. It starts from this home, moves into this white face, and it sees a black face, so it moves into here. And then it cannot move anymore because it's got no black faces adjacent to this white face. So it stopped. And the same happens to this guy, the same thing here. So I've glued all these, all these things together to form this. But if you follow through the argument I used to show that this is not possible, you see that such a thing is it's not possible. Okay, so this is idea. So using this, we're able to show that the curvature is at most -1, which is really what we needed to conclude that this group has a linear then function, and that is it. Okay, so this paper is on the archive, and if you want to have a look at it, and you can Google it. Okay, thank you very much.